All right, using the antiderivative with a second derivative. So there's no real difference. To do the antiderivative to a second, it would just take us to the first derivative. So we would end up with f prime of x, just 1. And then we do what we've done before. So that's 7 over 7, put a 1. Minus, and then we're going to get x to the 5th with a 5. Bring down the 4. And then that would be an x squared with a half. Bring down the 1. Plus x, and then again, plus c. So this is where the new thing occurs. But let's double check our work. So that would become 7 over 7, perfect, x to the 6th. That would be 4x to the 4th, perfect. That would be x period, and then a 1, and then a constant. So it checks perfectly. So now when we do our second derivative, do this in black, our new function is going to be the exact same thing we just did. Oops, why is it so large? I don't know. Let's rewrite it smaller. There we go. But now you'll see a little change at the very, very end. So this is 8. And so then we'd end up with 1 over 7 times 8. There's just 2 at the bottom now. Minus, and then this would be 6. And so this is 4 over 5 times 6. You just reuse the original fraction. And so this would be 3. 1 over 2 times 3. So I hope we can see that. There's the 4/5. There's the 1/2. There's the 1/7. I'm just putting the 8 and the 6 and the 3 right under it. So then this would become 1/2 x squared. And so now with that c, remember at constants, we put an x next to them, right? So if it was 1, we put x. So if it's c, we're going to write c, and then x, and then now what we have to do is actually add another letter. So I'm going to put it in as a little bit lighter shade, and I'm going to call it d as our new constant. And there you have our second derivative. We still need to simplify it, but so f of x is equal to 1 over 56 x to the 8 minus, and then the 2 and the 4 and the 6 will reduce. It's a 2. So we end up with 2 over 15 x to the 6 plus 1/6 x cubed plus 1/2 x squared plus cx plus d. So you end up with 2 constants because you got to take the antiderivative twice. So you're going to get 2 constants from it. Another thing to look at too is if you think about it, every single time we took the derivative, we're losing a term because it's a constant. So this one, we lost the d off the first derivative, and our cx became just c. And then taking the derivative for the second time, it would be gone completely. So if you have a second derivative and you have 1, 2, 3, 4 terms, make sure at the very end you have 6 terms, one for that cx and one for that d. Now, let's look at another one. So just like before, if you have a c and a d, then we're going to need 2 points. So we have 1 to find c, and we have 1 to find d. So they have to give you 2 points. And you can also do it with just plain old x and y, but that's a little bit trickier. So let's find first our first derivative. So if we start with a constant, we know it's 2x plus c. So if I take and I plug in my 2, I should end up with 5. So this would be 2 parenthesis 2 plus c. So that's 5 equals 4. And then subtracting the 4 over, we end up with 1. All right, now this should make sure, we always want to make sure that what we have is correct. So this is 2x plus 1. So now to check, and then we'll erase it at the end. We'll erase it right after it. F prime of 2 is equal to 2. And I plug in 2 plus 1, and I get 5. So that checks perfectly. We know we're good. Let's move on to the next part. We can now find our first derivative. So f of x is equal to, and again, this is x squared over 2. And we bring down that 2. And then we have a 1, so that would be 1x. And then now we're going to put plus d. And let's rewrite it. So this is f of x equals x squared plus x plus d. And we're going to stop and check. So that would be 2x, check, plus 1, and then the d disappears. And so now we can plug in f of 2 and find our d. F of 2 is equal to 10. which is 2 squared plus 2, put it in parentheses 2, why not, plus d. So we end up with 10 is equal to 4 plus 2, which is 6, plus d. Take away 6, and 4 equals d. And so now our function, f of x, is equal to x squared plus x plus 4. And again, we have to check. So we plug into 2 squared plus 2 plus 4, and that should be 10. So 4 plus 2 is 6, plus 4 is 10. Checks perfectly. If we take the derivative, we get 2x plus 1. Perfect. Derivative of that is 2. This is our function. It meets all of our criteria. Check, check, and check. All right, so now let's try this in application form. So a particle is moving with a given acceleration of a of t equals 2t plus 1. And we have the velocity at 0. So this is our initial velocity, and this is our initial position. So now we're going to find the position of the particle, the function for that. Okay. So again, with acceleration, if we take the antiderivative of our acceleration, it will give us our velocity. So we're just working our way backwards. So normally it was s, and then s would become v, and then v would become a. Now we're given a, and we're going to go backwards. So v of t would just be the antiderivative. So this is t squared, and we put a 2. We bring down the 2, plus, and then again that's a constant, so we're just going to put, I'm going to just put t now. I think we're good. Plus c. And since we know the initial velocity, we can find our constant. So our initial velocity was -2. And so if we plug in 0, because that's our t value, it will give us c. So you can see that c is equal to -2. So our new velocity function would be t squared plus t minus 2. And again, we should check this. And it's a very quick one. So if we take the derivative, we get 2t plus 1. And if I plug in 0, those 0 out, and I get -2. So that checks perfectly. So now we can find our acceleration function. Our position function. I'm already wanting to go the other direction again. So we take our antiderivative again. So this would be t3 over 3. And then we put in the 1. Plus, and then this is t squared over 2. And we put in the 1. Minus 2t. And again, now we can put plus d. And so s of 0 is 3. So 1/3, and we plug in 0. So all those 0 out, and so we know that d is equal to 3. This is what's nice about using an initial. The time is 0, so when you plug it in, your d and your c are the constants that we're getting. So s of t is equal to 1/3 t cubed plus 1/2 t squared minus 2t plus 3. So this is our position function. So based on an acceleration that we can calculate, an initial velocity and initial position, we know exactly what our position of our particle should be. Okay, so we want to make sure that this is correct. So if I bring down the 3, it's t squared. Check. The derivative of 1/2 t squared is t, and that's minus 2. We already know that one works perfectly. Now if I plug in 0, those all 0 out, and I get 3. It works perfectly. So the applications for second derivative are going to be just like this. And then the same here. If you're not given an initial point, then you just use cx and d.